Welcome to our webinar. We are just waiting for the few final people to join, and we will be starting the webinar in just a couple of minutes. Thank you for your patience. Good afternoon once again, everybody. Thank you all for joining, and let's get started. Welcome to the Alarm Corp webinar. Today we are looking at optic fiber fundamentals. My name is Piotr Dolecki, and I am the National Product Manager for CCTV here at Alarm Corp. Okay, before we get into the actual webinar itself, first of all, just a little bit of housekeeping/organizing. By now, all of you should be seeing the GoToMeeting window on the right of your screen. Just a couple of points. Here you see the raise hand button. You can use that to signal me if you want me to pay attention or if you need to ask me a question. So can I get you all to verify that you can hear me and actually press the raise hand button now? Okay, great. I'm starting to see a few hands going up. Thank you very much. If you want to put the hands down, we can continue. Perfect. Right. Next is the microphone button. Now, for the duration of this presentation, you will all be muted, and there will be opportunity to ask questions at the end via the questions pane. So basically, you will be able to type in a question and then just hit the send button, and I will go through the questions at the end as I receive them. Okay. The agenda for today's webinar. We will cover the following: the operating principles of optic fiber systems, including single mode and multi-mode. We will look at the typical components of an optic fiber system. We will explain the advantages of optic fibers as they apply to CCTV systems. And finally, we will look at some of the potential problems, pitfalls, and limitations of optic fiber systems. Okay, let's get started. Optical fibers transmit pulses of light instead of pulses of electricity. It is the principle of total internal reflection, or TIR for short, is what keeps the light in the fiber. Now, total internal reflection works on the basis that light hitting an index boundary. And what we mean by that is the boundary between two dissimilar materials, such as air and water. If the light hits it at the correct angle, it is reflected back. So some of the images below show you what total internal reflection looks like in nature. And you can see here in this shot, the fish actually cannot see the person on the bank because of the way its line of sight is reflected back. However, the person on the bank can see the fish. So now if you look at that from the fish's eye view, you can see here where the turtle is. You can actually see the reflection of the turtle and on the bottom of the water surface. You can't actually see out. Now, if we translate that into shining a light, you can see here that the light strikes the water surface inside this tank and is actually reflected back. So that shows that total internal reflection works. Okay, right. Now, it is this principle of total internal reflection that is used with the glass and/or plastic to keep the light inside the fiber. And the way optic fibers are made is that you have a boundary between two different types of glass. So you can see here in this example, we are shining a green laser into a block of plastic. The laser hits the boundary between the plastic and the air and is reflected back and then back again, and finally it exits back out the perpendicular surface. If we then were to take this piece of plastic or piece of glass and fold it into or extrude it into a cylindrical tube, you can see the same thing, that eventually light hitting at a certain angle will be reflected back down the fiber. Taking this step further, you can see here, even if the fiber is bent to some extent, the light, because it hits within the right angle, it actually keeps propagating down the fiber and doesn't actually reflect out. So once again, the way optic fibers are made is it uses a special type of glass, which is then surrounded by a different type of glass to generate that index boundary, effectively a boundary between two different types of material. And it is this boundary layer at which the reflection takes place. Okay, so now let's take a look at what optic fibers actually look at. So the images below show the construction of a single optical fiber and a finished cable on the right. In this example, we have the core and the cladding. The core and the cladding is the actual optic fiber itself, and the reflection, what we talked in the last slide about total internal reflection, actually takes place at the boundary between the core and the cladding. And this buffer coating on the outside, that is just there to effectively provide mechanical protection and stop the fiber absorbing moisture. The core and cladding is usually glass, although some short distance fibers are now made from plastic. The buffer coating is normally always plastic or some sort of elastomeric material. Now if we look at a finished fiber, you can see this is actually a bundle of optic fibers, and notice that we've got a bunch of yellow Kevlar fibers surrounding the optic fibers themselves. The reason Kevlar is used in this example is because Kevlar has no stretch, so it's there effectively to provide a measure of mechanical protection to the fiber. The thing to watch with optic fiber cables is that they do have a minimum bending radius. And if you've ever driven along the road, you may have seen these very, very large drums of typically blue or yellow colored, fairly thin cable that Telstra or Optus guys are feeding down into the pits. And you'll see that they seem to be going quite slowly. The reason they are doing that is because they are feeding optic fiber, and they are just taking more care with it. So yes, optic fiber can be broken, but normally if it's handled within the specification, it is quite robust. Okay, so there you have it. This is what a single optic fiber looks like and what an actual finished optic fiber cable looks like. Okay, now let's look at the light sources that are used for optic fibers. Typically, we use either light-emitting diodes, LEDs, or laser diodes. Now you see here a photo of a normal light-emitting diode. The diodes that are used in optic fibers are basically just high-quality versions of a standard light-emitting diode. If we look at a laser diode, though it is compared in size to a AA battery, you'll see that the laser diode is a little bit more complex. Now, the typical wavelength of light that's used for optic fiber, it's in the near-infrared range, so it's actually invisible to the human eye. Now, the light source is monochromatic, and what we mean by monochromatic, it means that it uses a single color or a single wavelength. Now, in this example, I've shown green light. Obviously, the light used inside optic fibers is effectively dark red, not green, but I wanted to show you that what monochromatic light looks like in practice. So it is a very single, very well-defined wavelength, and there are some very good physical reasons why that is, and that is to do with the material properties of the optic fiber. Now, light-emitting diodes are typically used with multi-mode fibers, whereas laser diodes are typically used with single-mode fibers, and we'll cover that on the next slide. Okay. Let's look at multi-mode and single-mode optic fibers and what are the differences between the two. If you look at multi-mode optic fiber, the core diameter is relatively large relative to the overall fiber diameter. And what that means is that multiple beam paths or multiple modes are possible. And you can see here in this example where we're showing a symbolic light source that the light can travel straight down the fiber, or it can bounce around up and down the walls, and obviously multiple reflections are possible. The light source for multi-mode fiber is, as I said earlier, typically a light-emitting diode, and the reason that is used is because a light-emitting diode typically shines a cone of light, and you see here in this example, the light-emitting diode has a 15-degree beam. And the advantage of this is that because we're firing a cone of light and we have a fairly wide core, the alignment of the light source to the fiber is not as critical. If we look at a single mode fiber, the core is very, very narrow, and what that effectively means is that the only light mode or only mode of propagation that's possible is the light that travels straight down the core and doesn't really bounce off the boundary so much. So in this instance, in single mode fibers, we typically use a laser light source. Now, a laser light source gives us a very narrow, highly collimated beam that concentrates all of the power into one very narrow beam. So a laser diode is not necessarily more powerful than a light emitting diode. It might emit the same amount of total light, but it just focuses that energy into a very, very narrow beam. Now, because the core of the single mode fiber is relatively narrow, and also the laser light beam is very, very narrow, the alignment of the laser light source to the fiber is critical. Okay, now you see in the bottom of this slide, it gives you a relative idea of what a multi-mode fiber and what a single mode fiber would look like. In the multi-mode fiber, the core is approximately half the overall diameter of the fiber, whereas in a single mode fiber you'll see that the core is less than 10% of the total fiber diameter, and the dimensions there are in micrometers. So if we look at some of the advantages of multi-mode fiber systems, LED light sources are cheaper to manufacture than laser light sources. Because the alignment of light source to fiber is not as critical, you can get away with lower tolerances, and this makes both the sources and the fiber connectors cheaper to manufacture and easier to manufacture. Therefore, a multi-mode system will have an overall lower cost than a single mode system. Now, if you look at the disadvantage of a multi-mode system, it will have a overall lower transmission distance than a single mode system. And typically for multi-mode systems, the maximum transmission distance ranges from a few hundred meters to several kilometers. Now, to give you an example of that, if you were to look at the data sheet for the latest IFS SFP optical fiber modules that are used with the network switches, the most basic multi-mode SFP module can go up to 200 meters. Whereas the next one up goes up to 2 kilometers, which is more than adequate for a typical network. If we look at single mode optical fiber systems, the biggest advantage is that the absolute maximum transmission distance is significantly longer than in multi-mode fiber. And the multi-mode system will go from, the single mode system can range from several kilometers up to tens or hundreds of kilometers if you're looking at the long-haul optic fiber links between capital cities. And again, if you look at the data sheet for an IFS SFP module in the single mode version, it can go from 10 to 20 kilometers typically. So you can see that straight away there is a much longer transmission distance that is possible with single mode systems than it is with multi-mode systems. Now, some of the disadvantages of single-mode systems is that the laser light sources are more expensive to manufacture, and that the alignment between the light source and the fiber is very critical. So this means that we need much tighter tolerances on the connectors, and because we're talking about tighter tolerances, this automatically increases the manufacturing cost. So overall, a single-mode solution will give you longer distance, but it will have a higher cost. And if we look at most CCTV systems, typically we're only interested in going for a few hundred meters. For that reason, multi-mode is more common in CCTV use than single mode. Okay, we talked about optic fiber construction, we talked about the light sources. Now let's take a look at signal loss and degradation within optical fibers. So just like in a normal electrical cable, the optical signal inside a fiber degrades as it travels down the fiber. Ultimately, the transmission distance is limited. So let's look at the three modes of signal degradation, which occur simultaneously. We have absorption, we have dispersion, and we have pulse spreading. If we look at absorption first, the optical fiberglass is not 100% transparent. And the best analogy to think about is a window. If you see a window glazer transporting a single window pane, it looks virtually clear. Yet if you see 10 or 20 window panes stacked together, you can see that there is a window pane because the glass appears darker than the surrounding air. So this is similar to the electrical resistance inside an electrical cable, that any light pulse transmitted into the fiber will be received at the end of the fiber as a weaker, dimmer pulse. Effectively, the light is absorbed by the glass. Next, dispersion or scattering. The optical fiberglass material is not 100% homogeneous. There are actually some imperfections within the glass. Also, the surface between the core and the cladding is not perfectly smooth. There are very small imperfections. And these combine to cause random irregular reflections, effectively scattering the light out of the optic fiber instead of propagating it down the fiber. So again, what actually happens in practice is that some of the light that is sent down the fiber ends up being reflected out of the fiber by the surface irregularities. And you will see an example of that in the next slide. Finally, we have pulse spread or modal dispersion. And this affects multi-mode fibers more than single-mode fibers. The light traveling down the optic fiber can take several different paths or modes. Each path has a different physical path length. Now, because of this, the speed of light within the fiber is constant, which means that a longer path will have a slightly longer total transmission time. So photons sent together by the transmitter arrive at different times at the receiver. And you can see an example of this in the little animation at the bottom of the slide. So the photon, effectively the light pulse widens or smears as it travels. Now, this pulse spread affects multi-mode fibers more than single-mode fibers because you have more modes possible, and this is the key reason why multi-mode fiber is limited to shorter differences than single-mode fiber. Okay, I talked in the last slide about this dispersion, and you can see here an example. This is actually at the glass structure level, and we are seeing that incident light, symbolized by the three thick beams, ends up being scattered out. And if you look at the two photos next to it, notice that the plastic through which we're shooting the green fiber actually seems to be glowing. Notice also on the right hand where we show this blue fiber, it's actually glowing blue. Now this is great for a Christmas decoration, but it's actually not what we want in an optical fiber, because the fact that we're seeing this light, the fact that we're seeing the material glowing, it means that that light is being radiated out of the fiber instead of being propagated down the fiber. So this is what we mean by scattering. The light's being scattered out instead of arriving at the other end of the fiber. And if we look at the little image at the bottom, where we see dispersion, this spreads the pulse. We fire two pulses, one after the other, representing binary value 1 and then 0 and then 1. Effectively, all of these means of signal loss combine that at the receiving end, the pulse is weaker, and because of the spreading, where we should be receiving no light in the middle between the two pulses, we're actually getting a little bit of light. And depending on your logic thresholds, the system actually gets to a point where it can no longer discern between a binary level 1 and a binary level 0. And it is this that ultimately limits how far you can go, because if at the receiving end you cannot decode the signal properly, you will not be receiving a correct signal. Okay, putting it all together, if we look at the propagation of signal inside an optic fiber, we have an input pulse, actually two consecutive input pulses. As these two pulses travel down the fiber, some of the energy is absorbed, some of it's reflected out of the fiber. So we see that the overall strength of the pulse is getting weaker. This is symbolized by the lowered height. And because of this dispersion and pulse spreading, we actually see that the two pulses combine to look like one pulse at the receiving end. Now, having said that, bear in mind that the transmission distance possible with optic fibers is still significantly longer than possible with copper. As we said earlier, with a single mode fiber, transmission distances of tens to hundreds of kilometers are achievable. However, ultimately there is a limit, either because the signal is too weak or because it is no longer possible to decode the individual light pulses into their respective values. So okay, that gives you a very, very quick summary of what actually happens to the light pulses inside the fiber. Okay, now let's look at signal encoding and decoding. The optic fiber transmitter and receiver is often called an optic fiber modem. The input signal to the optic fiber modem can be analog, as in composite video, or it can be digital in the case of serial telemetry for PTZ control, or TCP/IP traffic in the case of optic fiber networks. The optic fiber modem encodes or translates the signal, the input signal, into optical pulses that are fired into the fiber. Now, the optical signal can be analog. For example, in the old IFS, the VT/VR series, the signal was frequency modulated. The optical signal can also be digital, either 8-bit encoding or 10-bit encoding, which is used with the latest generation IFS signal. The optic fiber decoder or receiver receives the signal and then decodes it back into its original format. Now, this can be either back into composite video or back into RS-485 for telemetry traffic, or it can be back to TCP/IP Ethernet traffic out to an RJ45 connection, depending on the optical fiber modems in question. And if you look at the IFS range, various combinations are possible. There are devices for encoding analog video, devices for encoding serial telemetry, devices for encoding change of state, such as alarm contacts, and so forth. Now, having said that, it is important to match the receiver and the transmitter so that both are expecting the same signal type. In other words, if you're having a 10-bit digital transmitter, you will need a 10-bit digital receiver. If it's a frequency modulated transmitter, you need a frequency modulated receiver that's designed for the same wavelength. Now, digital encoding can offer better image quality in CCTV because with digital signals, error correction is possible. Error correction is not really possible with an analog signal. So this is one of the big advantages if we look at the new IFS platform, why it can give you better image quality than the previous generation, because we are dealing with a digital signal transmission medium. Okay. Typical optic fiber system components in CCTV. And here we have a very, very simple system. We have an optic fiber transmitter that converts the composite video signal into light pulses, launches it down the fiber, so we have an analog camera connected via coax cable to the VT1101 transmitter. A multi-mode fiber is connected to the transmitter. It goes down its optic fiber conduit and is connected at the receiving end into an optic fiber receiver. So the optic fiber receiver will convert the signal back into a composite video signal, and in this case we connect the BNC video to a digital video recorder. Now, this system shows an analog video transmission. However, the same would hold for a network transmission system, as we see here. In this case, we have a couple of IFS network switches. Both have the capability to have an optic fiber uplink. So we plug a suitable SFP module into the switch. The optic fiber is then plugged into the SFP module at the transmitting end, and at the other end into the receiving SFP module. So in effect, we are now using optic fiber to transmit TCP/IP traffic over using the optic fiber encoders. Okay. Now, if we look at typical optic fiber systems in CCTV, many system configurations are possible depending on the application. We showed you the simplest single-channel one-way video over a single optic fiber, as per the previous slide. Next, we can have a single-channel video with return data, in this case PTZ telemetry, where we want to control a PTZ speed dome. We can do that over one fiber, or we can do single-channel video with return data over two fibers. In this case, we would have effectively a dedicated video fiber and a dedicated telemetry fiber. We can also have multi-channel video over a single fiber. In this case, we multiplex two or more video channels onto the one fiber. Likewise, we can have multi-channel video with multiple PTZ telemetry over two fibers. So these are just some examples of the typical systems that you are likely to see in video surveillance. Okay, let's look at some of the advantages of optic fiber systems as used in CCTV. The first and biggest advantage is that longer runs are possible than either with coax or UTP. Now, even if we look at IP cameras today, a single Cat6 run is limited to a total length of 100 meters. Typically, that's written as 90 meters plus 10-meter patch lead. If you're using PoE cables, or PoE cameras, you may need to be even closer because of the power consumption of the camera. With analog video over RG59, you typically don't want to go longer than about 150 meters. So if you do need to go longer, this is one of the key advantages of optic fiber systems. Optic fiber preserves video quality over long cable runs. And in the context of a long camera run where we're talking about 200-300 meters, over that sort of transmission distance, you will get virtually no video quality degradation over the optic fiber, whereas you would definitely see a degraded video signal if you try to run coax that length. Now, multi-mode fibers can do up to several kilometers. Single-mode fiber can be tens of kilometers. So this is well suited for larger sites, such as airports, such as seaports, or freeway traffic monitoring, such as if you look at, say, Eastlink in Melbourne, M7 in Sydney, all of those sort of applications where you have very long distances between the camera and the receiving stations. This is only really possible with optic fiber. The next biggest advantage, optic fiber is immune to any interference, whether we're talking radio frequency interference or electromagnetic interference from electrical machinery. So if we're looking at noisy sites such as power generation, energy substations, factories which may have welding machines or variable frequency drives for electric motors, iron ore smelters, aluminium smelters, public transport such as electric trams and trains which use variable speed drives, also telecommunications infrastructure where you have a lot of microwave radiation, as typified by the mobile phone base station. In all of those types of applications, you have a lot of sources of potential interference, and if you run video over optic fiber, then that is no longer a problem. But by far the biggest advantage is that optic fiber cable electrically isolates the cameras from the recorders. And this is really important for areas that are subject to lightning strikes. Let's say you have a jail or an airport in an area where there is lightning strikes possible. You have a camera mounted up a 30-high pole. The pole being the highest object around is most likely to be struck by lightning. If it does get struck by lightning, then the lightning strike will typically destroy the camera, and it'll typically also destroy the optic fiber transmitter, but nothing else. If you had this system where you had a traditional camera and it's wired by coax back to the central server room and you get the lightning strike, the following will happen. The strike will destroy the camera, but then the lightning strike, this surge of energy, will travel down the coax or Cat5 cable, and it'll end up getting back to your equipment rack. Your camera will be destroyed. The equipment rack is likely to suffer damage. But the biggest amount of damage is that the cable itself will be burned and destroyed, or damaged to the point where it's unserviceable. Now, replacing a camera out on the pole is obviously expensive. You need to get a cherry picker or a scissor lift. Replacing the equipment in the equipment rack is also expensive and takes some time. But replacing the buried cable may no longer be possible. Imagine if this is a cable that's running under the new runway at Tullamarine Airport. Imagine if it's a cable that's running under a major freeway. And in order to get to the cable, you've got to dig up either the runway, dig up the airport apron, or stop all traffic on the freeway. It's, in these sorts of situations, there is simply no practical way to replace the cable. If it is an optic fiber, because optic fibers cannot propagate electricity, the fiber will be undamaged. And all that you would need to replace is the camera itself and possibly the optic fiber modem at the transmitting end. So if you're looking at these sorts of sites, yes, installing optic fiber will add some additional cost to the overall project. But then it becomes absolutely critical to perform a risk analysis and decide if something happens. First of all, how likely is my site to get struck by lightning, and what are the consequences of that strike? And of course it will be different for each site, but in some sites, this is the critical consideration. Okay, now let's look at some of the pitfalls and problems. And we can divide these into two. We have system design problems and what I call installation problems. If we look at system design problems first, mismatch as in selecting multi-mode transmitters and receivers to use with single-mode fiber or vice versa. So when you're planning a project, we need to be clear, am I using multi-mode fiber, am I using single-mode fiber, and then pick the modems to match. Mismatch as in mixing incompatible receivers, picking a receiver from one family and a transmitter from another family, and the two simply are using different formats or different wavelengths. Now, in the case of the new generation IFS system, the system has been explicitly designed to be modular, so it is possible to change from multi-mode to single-mode via an SFP module, and that does take away a little bit of that system design mismatch problem. This was not the case with previous generation optic fiber systems. If we look at installation problems, mismatch of patch cables. Typically a patch cable is used between the main cable and the actual receiver. If you mismatch a single mode with a multi-mode or vice versa, the signal may simply be too weak to be received at the modem. Next, we have optical fiber cable damage by ignoring the minimum bending radius, by twisting or by stretching the cable. If you exceed the bending parameters of the cable, the actual glass inside the cable starts breaking, and the result is a broken optical path. Next, we have optical fiber cable damage during or after installation due to either what I call a bobcat or a bulldozer error. The result is above. Now, this can also happen maintenance down the track. The local council workers are trying to dig up a pipe and they simply cut the cable. Either way, the optic fiber cable is cut. The damage. Now, what happens then? You can repair a damaged optic fiber cable. It is possible to resplice the cable. There are professional machines that do this. However, each resulting splice introduces additional signal loss, and you can get to the stage where there are just too many splices in the cable and the resulting optical loss is too high. And finally, if we look at poor quality patch cables or dirty connectors, these can introduce signal loss. Now, in particular, dust on a patch cable. Remember, we're dealing with a very, very thin cable, and at that level, even a single speck of dust can introduce a lot of losses. So these are the typical pitfalls and problems that are likely to be experienced with optical fiber systems. Having said that, they are typically very, very easy to commission. Normally, the optical fiber cable is laid, it's commissioned, and you simply plug in the transmitter and the receiver, plug in the power supply. You will typically get a LED that says, yes, I have power. Then you will have a second LED that says, yes, I can transmit. At the receiving end, you will have a LED that says, yes, I have power, and a second LED that says, yes, I am receiving a signal. So it is very much a plug-and-play system. And unless the cable is damaged after installation, optical fiber systems typically do not need any maintenance. It's simply plug and play and off it goes. Okay, so let's summarize what we just covered. Optical fibers work on the principle of total internal reflection to propagate light down the fiber. We have two types. We have single mode and we have multi-mode. Multi-mode systems are typically less expensive, whereas single mode systems typically cost a little bit more but permit longer transmission distances. Both multi-mode and single mode allow significantly longer transmission distances than are possible with copper. Optical fiber gives you higher transmission speeds, particularly if you're using it for LAN backbones. Optical fiber systems have interference immunity, very well suited for electrically noisy environments. Optical fiber systems have lightning immunity, and this reduces maintenance and repair costs on sites that are subject to lightning. Optical fiber systems do require a little bit more care during cable installation and termination. However, they are fast to commission and plug and play. And as technology changes, it is often possible to upgrade the transmission system by simply replacing the transmission and receiving modems at either end without touching the fiber itself. Okay, now just to give you some idea, in the current IFS range of network switches, virtually all of the switches have got the capability to provide an optic fiber uplink / backbone. Likewise, in the new IFS optic fiber transmission range, there is a complete system in both multi-mode and single mode. And there's actually a very, very intelligent management module which gives you real-time diagnostics of the system. Now, if you want more information on these products, please send me an email at your convenience. Okay. Would you like to know more? More information, including brochures and data sheets, may be found on our website, alarmcorp.com.au. It may also be found on the GE Security website. I would invite you to subscribe to the Alarm Corp Pulse to receive new product information automatically. If you register online with alarmcorp.com.au, you can get full access with our e-commerce platform, including your own customized pricing and order placement, which means you can then place orders 24 hours a day at your convenience. Please contact your nearest Alarm Corp representative, Jeff Rushton in Sydney and Stephen Dinger in Victoria and SA. The emails are listed, as are the mobile phone numbers. And you can contact myself, Piotr Tolecki, direct on 0421 378 334, and my email address is prd@alarmcorp.com.au. Now, thank you for your time. This concludes, I guess, the content of the presentation. Now, I said earlier about registering online. If you do register online, you will get and place your first online order. You will get 10% off during May for your first order. And just to give you some idea, we do have a range of other products such as DVRs, cameras, monitors, and we are doing some very attractive end of financial year specials. And this gives you some idea of what is available. We have more products available, so please contact us for more details. Okay, this concludes the webinar itself. Now over to question time. I would invite you all to look at the question tab and type your question, and remember to hit send on the bottom. Okay, the first question is the Queensland contact Ed Savaris? No, Ed is no longer with Alarm Corp. However, stay tuned for more information. Right, next question. Do you have to use the same size patch lead, i.e. cable run is 50 but patch lead 62.5 or vice versa? Very good question. Most of the cable today will be 62.5 micron. I would say, where possible, you should use the same diameter patch cable. However, for short distances, you may get away, but that's something I would check with the depends on application. In general, most of the IFS range is rated to use either 62.5 micron cable in the multi-mode application. So it is always possible to match the cables. I hope that answers that. Okay. Should I deal with the New South Wales rep for Queensland inquiry? Yes, at the moment, please do. Please contact Jeff Rushton for more information. Okay, so hopefully that's answered the question thus far. Okay, next question. Here we go. Where can you buy the optic fiber cable itself? Do you sell this? No. Alarm Corp sells the optical fiber transmission equipment. From the IFS range optic fiber cable itself, I would suggest you would need to contact a dedicated cable company that actually makes the cables themselves. Okay, right. Do TCP IP fiber modems support auto crossover like Ethernet? That's a very good question. I would say that Almost certainly yes with the latest devices. However, you would need to double check on the data sheet that's relevant to each product type. So if you have a specific product in mind, I can check that for you, but most of the network devices these days are tend to be auto configuring. But if you send me an email on that question, I can actually send you a data sheet and we can look at that in a bit more detail. Okay. Are there any more questions? Right. Can you please put up your contacts again? Hang on just a second. Previous. There you go. Hopefully all of you are now seeing the contacts on screen now. Okay, the question is Alarm Corp continuing to support ST connectors or moving towards LC connectors only? Look, if you look at the data sheets on the new IFS range and including the SFP modules, we have models that support both at this stage, and that really again does vary by model. At the same time, there is a range of connectors and adapters available which do allow you to go ST, LC, and vice versa. So those are now listed in our current trade prices. So I can double check it, but from what I've seen, the data sheets on the devices, they support both types. Okay. Look, if there are no more questions at this stage, I would like to thank you all very much for your participation. Now, this webinar will be available. It has been recorded and will be available on our website for you to be downloaded at your leisure. So if you want to recap, go over anything else, you can download the webinar. You have my contact details. If you have any specific questions, please feel free to email me. Otherwise, thank you all for your time.